Okay, so today we're going to look at cyclotrons, which are a really great example of how electric fields and magnetic fields and the interaction with charged particles can be really effective in science, and particularly for making medical isotopes that are radioactive, that are used a lot and are really, really important. Now, what are cyclotrons? Basically, cyclotrons are used to accelerate ions to very high speeds. And what they do is after these ions are at high speeds, we collide them or crash them into other nuclei to produce radioisotopes. They can be used in medicine and industry. Okay, so if you are going to get a scan of a certain type of cancer, or you want to look at a specific organ, that's where we use cyclotrons to create these radioisotopes. Now, these are usually located pretty close to the hospital or the treatment facility you're using. And the question is why? Well, basically, we're creating radioactive material. Now, radioactive material decays, so we want it pretty close because if it decays, it's useless. Okay, we need it inside the body or in its particular function before it decays. After it decays, it's not going to be very helpful for us. So that's why we have to build these really close to the place we need them. And this is just a picture of a real-life cyclotron. Now, what we've got here is a side view of a cyclotron. We're going to be more interested in a top view, but for now, let's have a look at the side view. So what we've got here is the ion source. So we're going to send our ions in this way. They come into our cyclotron, and they're met by this magnetic field. Okay. Now, we can already tell that this is the velocity of our ion and our magnetic field are at right angles. So we're going to get circular motion, which is exactly what we want. Now, our ion source goes into these, what we call Ds, and from above, we'll see why these are called Ds, because they're shaped like Ds, spoiler alert, but these Ds are located in a vacuum chamber, and that's just so we can go around and our ion sources don't crash into anything apart from the target. So the trick with this one is we're moving at right angles. We have a magnetic field set up between the top and the bottom, and we have these Ds, which are in a evacuated chamber. So this is a look at the cyclotron from the top view. So we can see these are the Ds so far. I've just got two Ds. Now, inside these Ds, there's no electric field because these are hollow conductors and we know they don't exist. But we do have this magnetic field. And because we're looking at it from a different angle now, this magnetic field is running into the page. But it's exactly the same as what we saw on the other side, except we're looking from the top now. Okay. So the first thing we have is this magnetic field. The next thing we have is one of these sides is charged positive, and one of these sides is charged negative. Okay, now that creates an electric field, and our electric field goes from positive to negative. So let me draw this electric field here. Okay, and it runs this way. Now what we see is the entire D is charged, but like I said, it's hollow. So the hollow conductor, we know there's no charge inside a hollow conductor. So the electric field only exists between these two Ds. So the way a cyclotron works is we release somewhere near the center a particle with some charge. And let's say this one is a positive charge because it works for our situation. So what we get is our positive charge is attracted to the negative, so it moves this way. And as soon as it gets past here, it enters this no charge region. Okay, so what happens is we've got a positive charge moving towards the right, a magnetic field into the page, so we get a force acting upwards, and we see this circular motion coming into a play. So our force acts this way, and it acts all the way in towards the center, and we get the circular motion, and what we get is our particle come back to the center. Now, we've got a positive charge here now, so all it's done is travel from one side to the other, turned around, and it's back here. But now it's next to the negative. So what our cyclotron does, and the way it works, is the signs flip. So this side becomes positive, and this side becomes negative. Okay, now we can accelerate across here, and we get faster as we move across here because we've already got some speed, and then we pick up extra speed. What that means is our circle becomes larger. And again, we get back to the other side and we flip. We become positive again. This side becomes negative again. So we get faster across here. We keep accelerating across this gap. And we keep getting a bigger circle and we flip, bigger circle, flip, bigger circle. And this happens until our radioisotope is at our desired speed and it is released out of an exit tube and crashed into our target here, which creates our medical isotope. Okay, but that's how a cyclotron works. So the process, so exactly what I've just described, but if you want to have that in a written form, there's a charged particle, it's usually a proton, so I got that one right, is introduced to the center of the cyclotron between the Ds. The particle is accelerated by a uniform electric field, so that's the electric field that we drew out, and it gains kinetic energy, gains speed. So once inside the Ds, there's no electric field, hollow conductor. We got that one. The magnetic field causes the particle to travel in a circle, bending it back towards the gap between the Ds. So we get that circular motion. Now the potential difference between the Ds is reversed, so that the negative becomes positive, positive becomes negative, and we're attracted to the other side. And the process repeats, and each time we do it, the path gets larger until our proton can reach the target, just as we drew out. This is just the word form of exactly what we drew. All right. Now let's have a look at some maths. And I know, first of all, what you're thinking is, how did he get over here in the bottom left corner? But just magic. Now the next thing is the time taken. So what we want to do is we want to use some of the properties we know about circles. So we know the circumference of a circle is 2 pi r. So if I just want to look at one of these Ds, I can take half of the circumference. So divided by 2, I get pi r. So the distance around half of a circle is pi times r. Now we also know the time is equal to distance divided by velocity. And if I put this in for my distance, I get time equals pi r on v. However, I also know from a previous video that r equals mv on qb. Now I can put this straight down to here. And, well, actually, the first thing I'm going to do is I'm going to rearrange so v is by itself. Okay? Now, I can put this v down here. And what I get is my time equals pi rm over r qb. The r's are going to cancel that. And I get the time it takes to go around one of these Ds is pi m divided by qb. Now, because this is only half a D, if I want to work out the full circle, this time is equal to 2 pi m over qb. So all I've done is times this by 2 to get the full circle. All right. This is the time it takes for our particle, our proton, to go all the way around the cyclotron in a circle. And that's really important, and we're going to use that in an example later. All right, we have another equation, and again, bottom right. Crazy, it just keeps happening. So we know that the kinetic energy is half mv squared, and we have this equation that relates our v again. So we're going to rearrange for our v. And all we're going to do is chuck that v back into our kinetic energy equation. And what we can do is we can derive this is our kinetic energy for our particle. So it's related to the charge, the magnetic field strength, the radius of the circle, and divided by the mass. Now you can see here, and a really important concept is that the kinetic energy doesn't actually depend on the velocity of the particle, just on these aspects here. All right, let's have a look at an example now. So we've got a cyclotron used to accelerate deuterons of mass 3.34 times 10 to the negative 27 kilos. The radius of the cyclotron is 30 centimeters, and the magnetic field strength applied has a strength of 1.6 teslas. So let's write down what we know. So we know the mass is equal to 3.34 by 10 to the negative 27 kilograms. We know that the magnetic field strength is 1.6 teslas, and we know the radius equals 0.3 meters. Okay, we know a couple of other things, and let's show how we work those out. So the first thing we have to do is we have to assume that the deuteron is an ion, so its charge is just the proton in the center, so 1.6 by 10 to the negative 19 coulombs. And then we can just use our equation for the period, so 2 pi m on qb. So period equals 2 pi m over qb. Substitute that in, we've got 2 pi times 3.34 times 10 to the 27, negative 27, divided by 1.6 times 10 to the negative 19 times by 1.6 Teslas. If we put that into our calculator, so that gives us 8.20 by 10 to the negative 8 seconds for it to complete a period in the circular path. Now, we also want the kinetic energy. So I'm just going to break this up a little bit. So we know the kinetic energy from our previous page is this one down here, Q squared B squared R squared over 2m. So kinetic energy equals Q squared B squared R squared over 2m. Now you might also see this written as E with a lowercase k. That's also kinetic energy. So if we substitute in these points, we've got 1.6 by 10 to the negative 19 squared times by 1.6 squared times by 0.3 squared divided by 2 times by the mass, 3.34 by 10 to the negative 27. And if we substitute this in our calculator again, we'll get which equals 8.83 by 10 to the power of negative 13 joules. Energy is always measured in joules, but we've been asked to find it in electron volts. Now, to go from joules to electron volts, we divide by 1.6 by 10 to the negative 19. And our answer is going to be 5.52 by 1, 2, 3, 4, 5, 6, 10 to the power of 6 electron volts. Awesome. So that's how we deal with those problems. And kinetic energy. So just want to highlight one fact. So the kinetic energy is actually independent of the potential difference across the Ds. So no matter what the potential difference is across the Ds, it doesn't actually affect our kinetic energy. You can't find it in there. So it depends only on the magnetic field and the radius of the cyclotron. Okay, so thank you. And that is the end of our look at the cyclotron.